Number 3. One type of BB gun uses a spring-driven plunger to blow the BB from its barrel. Letter A. Calculate the force constant of its plunger spring if you must compress it 0.15 meters to drive the 0.05 kilogram plunger to a top speed of 20 meters per second. All right, so force constant is just another name for a spring constant if you want. So you know we have two formulas here. F is equal to negative kx, that's Hooke's law. And then the potential energy formula, that potential energy, the elastic potential energy, that is 1/2 kx squared. So given the information that's in the problem, okay, it's probably easiest to work with the potential energy formula. All right, because you'll notice it's going to be very hard to come up with the force at the moment. So if I write down now the potential energy, right, the potential energy, the elastic potential energy, I'll say, is equal to 1/2 times the spring constant of the spring multiplied by the change in displacement, okay, or just the, I'm going to leave it as change in displacement of that particular spring squared, all right? This is, the delta x is basically the amount it's compressed or stretched, okay? The question now becomes is I have to solve this. They want to know the force constant, so I have to solve this for k. So why don't we just reorganize it first, okay? So we know that k then will equal, just doing some algebra here, the k will then equal 2 multiplied by the potential energy, right, of the spring, all divided then by the change in displacement or the amount of compression squared. Now, we know how much it's compressed. I mean, it told us it's compressed by 0.15 meters. So we know this value here, the delta x. But do we know the potential energy? Well, we don't, okay? So we have to consider, right? Anytime you have energy in a problem, you definitely want to think about the basics, right? Energy is conserved, it's transferred, right? Assuming there's no friction, it's not lost, okay? So in this problem, there's nothing about friction. So what I realize is that the information they tell me here, that this BB, right, to drive this plunger, okay, sorry. The mass of the plunger is going to be 0.05 kilograms. And the top speed of the plunger is going to be 20 meters per second. So basically they told me a mass and a velocity. So now I'm thinking to myself, do I know a connection between mass, velocity, and energy somehow? I kind of do, right? That's the kinetic energy formula. So kinetic energy, I'll write it down here, is equal to 1/2 mv squared, right? So this tells me that if I know the mass of an object and the velocity that that object is moving, I know it's kinetic energy. So here's the key to the problem. It's the fundamental that there's conservation of energy. What that means is that the potential energy that the spring has within it when it's compressed will be fully translated into kinetic energy. So basically, that means that if I know the kinetic energy that the plunger eventually reaches, the total kinetic energy, the question, well, where did that kinetic energy come from? Well, it came from the potential energy that was inherent in the spring when it was compressed. Okay, you know that when the spring is compressed and you let go of it, you know there's going to be some translation of that pent-up energy, so to speak, into now this moving object. So that's the key to the problem. So I realized then that the fundamental connection in this problem is basically the conservation of energy. That whatever energy was lost by the spring, whatever potential energy was lost by the spring, was then gained as kinetic energy by the plunger, right? That's the basic idea. And I know that this thing, potential energy is going down, kinetic energy is going up, but we know that the sum of the energies basically is going to be zero, right? Energy is not created or destroyed, it's just transferred. So what that means is that the sum of the energies here is basically zero, all right? And that means then that the kinetic energy, that's positive, minus then the potential energy, which is, that's why it's minus, it's negative, will equal zero. That means that the kinetic energy will equal the potential energy. All right, so I'm basically now just going to simply plug this on in. So this is 1/2 mv squared. I can now plug that in for my potential energy. Okay, let me go the other way with this. Let me go that way. All right, now when we do that, let's write it out. So the spring constant is now going to be 2 multiplied by 1/2 mv squared, all divided by the change in displacement squared. Now you can think about it, right? If the plunger had some kinetic energy to it, where did it come from? Right? It's got to come from somewhere. It came from the potential energy that was pent up in the spring. You know, when you compress a spring and you let go of it, that potential energy gets converted into kinetic energy. So Anyway, the spring constant here is going to be 2, well, the 2 times the half just cancels, right? So I'm just going to cancel that. The mass then of the plunger was 0.05. The velocity was 20 meters per second. That's squared. And all divided now by the change in displacement is going to be technically negative 0.15, but the whole thing's squared, so it's just going to work out to be positive, which is good because k should be positive. So 0.05 times 20 squared divided by negative 0.15 squared. And it's going to be about 889. All right, 889 newtons per meter. And that's the spring constant. So that takes care of letter A. In other words, that's also the force constant, right? Tomato, tomato. So here, now let's take a look at letter B. So what do we have? What force must be exerted to compress this spring? So now I can use Hooke's law. That the force, right, needed to compress the spring, which is basically the force that the spring exerts on the, on the plunger, is going to be equal to negative K multiplied then by the change in displacement of that particular spring. So just solving this on out simply, it's going to be negative K, which is 889, times in the displacement, but that's again negative 0.15, right? So if you notice double negative, it's going to be a positive value, and that should kind of make sense for how I'm framing this problem. I'll draw a little picture maybe. 889 multiplied then by 0.15, so there's going to be about 133, and that is in terms of newtons, okay? Should be around there. I use the rounded value, but it should be fine. The basic concept is I'm saying here is, here I have a certain spring, okay? And then I have the spring and it's compressed now, okay? There's a little plunger. You can just show it as a little ball. It doesn't even matter what it is. But essentially the plunger here, this spring is now compressed. And notice I compressed it in the negative X direction, okay? So that's kind of why, that's how I'm thinking about the problem. I have a spring, it's then being compressed in the negative X direction. So when this thing becomes released, the ball moves to the right. That's why it had a positive velocity. And that is also why then the spring change in the spring displacement is negative, because I started at a positive and then I went to the left. All right. So guys, thanks for tuning in. Hope this helped. Please remember to subscribe and we'll see you next time. Take care.